first graph here, you can see all the equations here. And each of the graphs are labeled A, B, C, D, E, F. I put them on two separate graphs just because it would be too much to look at them all in the same. But I want to know what is similar, what is different for each of these. You can also look at the equations and sort of see what's going on with the equations as well. So if you want to chat with the person sitting next to you, you can do that. But how are they similar? How are they different? Take a couple seconds to look and put a couple things in the chart here. All right, so what did you guys discuss was similar between the two, or between all of the graphs? Jacob? Okay, perfect. So same x-intercepts. Okay, anything else the same, Clayton? Oh, same axis of symmetry. Bella? All degree 2. So they have the same degree, which is 2. Michael? Is that what you're going to say? Okay. They all also have same end behavior. I don't mean the end behavior of all of them is the same, but they're all U-shaped with the same end behavior. Some of them are 2 to 1, some of them are 3 to 4, but they're all same end behavior in the sense that, yeah, they are even functions or even degree. So they're all U-shaped, like facing up, or U-shaped facing down, right? Okay, what's different? Clayton?
Some are like skinnier and some are wider.
Okay, so some are stretched and compressed. Michael? Okay, so the first ones are all facing up, second ones are all facing down. So we could say like A, B, C faces up, or opens up, maybe we could say, would be a better description. And then D, E, F opens down. What else? Any other differences? So we said they had the same x-intercepts, but they have different y-intercepts. So the y-intercepts are different. Did we miss anything that's different about them? Clayton? Oh, the vertex is different. The x of the vertex is the same, right, for all of them, because they're all on the same axis of symmetry at 1, but the y of the vertex is different. So maybe we could even make that distinction. The x is the same, but the vertex, the y coordinate, is different. Okay, so we could make a general statement, and we can say no matter what k is, so no matter what the multiple is in front of our equation, like all of these, what could we describe is like a consistent relationship between all of these graphs? No matter what, they'll all have same x-intercepts. Or we'll say all graphs would have the same x-intercept. And I will say and the same general shape. Okay, and of course we can see from these binomials that we're getting x-intercepts that are the same from those binomials, so that should make sense. So this brings us to the idea of a family. So a family of functions will have the same characteristics, so same general shape is happening. Of course, if they have the same amount of x-intercepts with the same orders on those x-intercepts, then it will have the same overall shape. And polynomial functions with the same x-intercepts are said to belong to the same family. Or the same zeros, or whatever you want to call them. All right, so let's say we have a cubic function, and the zeros are 1, 2, and negative 3. If I were to create a general equation for this family, this is basically a general equation for this family above, right? It just gives k as like all possible multiples that could be in front of that equation. So how would I create a general equation if these are the zeros and this is a cubic? Bella, what would you do? Perfect. So general equation means we need to have some multiple out front that represents all the different multiples that I could have. So all the different members of the family are represented with this general equation. It can be p at x, it can be f at x, whatever you want. So that's our general equation. Now I want you to create two equations, so two functions that belong to this family. And all we need to do that is just choose a value for k. So two different members, write two equations that belong to this family. Okay, you might notice some overlap here with like some of the stuff that we talked about in Unit 1, because we did some of the solving processes for these. So Andrew, what did you pick for the k in your first family member here? All right, so maybe I'll change the name of the function. So we can have a member that is f at x, which equals a k value, which has a k value of 2. Jacob, what did you choose?
I chose 1/2.
Okay, perfect. So we can also have 1/2. Really, k can be anything, right? It can be negative, it can be positive, whole number, fraction, whatever. Okay, so as long as you plugged in something here and they were different, you're good. Okay, now we're going to determine the equation for the specific family member that passes through the point 0, 3. So if this is my general equation from above, how would I do something like this? Let's draw on some Unit 1 knowledge here. Kenzie? Okay, so we will evaluate p at the x value of 0. So I'm going to sub in 0 for all my x's, because that's the x coordinate of the point that I'm given. And I know the polynomial's value when x is 0 is 3. So I will replace p at 0 with 3. Remember, p at x just replaces y, right? It's the same thing, p at x and y. So basically, I'm just saying y equals 3 when x equals 0. Okay, let's simplify. We'll get -1 times -2 times 3 should give us +6. Then we divide. Be careful. This is not 2. This is 1/2. Okay, so final equation, you just plug that back in, right? Okay, we know how to do some questions like this, right? If we're given a point and we have to solve for k, we just plug it in and then simplify. Any questions for this one? So far, so good? Okay. Now we have a quartic function. Its roots are positive 1, negative 1, 2 plus root 5, and 2 minus root 5. This is a little bit different than some stuff that we've seen in the past. You might remember this back from grade 11. In our very first unit, we talked about like how we simplify radicals, and then we solved some equations, and we kept our quadratic formula in exact form. Do you guys remember doing that in grade 11? So when I say quadratic formula, I'm talking about this negative b plus minus b squared minus 4ac over 2a, right? So we plugged all our quadratic stuff in, we simplified, we kept it in exact format, and we got some stuff that looked like this. Sometimes it was over something else, sometimes it canceled out. That's where that comes from. So I'm getting 2 binomials from the positive and negative 1. I think that's pretty easy for us to figure out, right? We have p at x. This is asking for a general equation, so I'm going to put k here. And how do I create binomials from this information? Positive and negative 1 are x-intercepts. Clayton?
It would just be x plus 1 and x minus 1.
Yeah, so we just make binomials. We switch the signs that we see. But because there's a positive and a negative, we'll just put plus and minus there. Okay, now I'm going to get from this a quadratic function. It will not be a factorable quadratic function because this comes from the simplification of the quadratic formula. And I don't do that unless I can factor. So we're just going to do some work for this over to the side. What we do is we set x, which is the solution, equal to our intercept. And then we sort of like undo what we would do to solve for, or like isolate when we would have something in like standard form. So I just want to solve to get this equal to 0 to find out what this quadratic is. Okay? And the way we do that is we're just going to move everything over until we get 0 on the right-hand side. So I will do x minus 2 equals plus minus root 5. How do I get rid of a root? I square it, so we will square to get that 5 out of the root there. We get x minus 2 squared equals 5. Positive squared and a negative squared, they both give us a positive, right? So this will just sort of cancel out. Okay, and then I will bring this over. And then the last thing I'm going to do is I'm just going to expand this out so I can write the full quadratic, simplified quadratic there. Because this is sort of like in a vertex type form right now, and that's not really ideal for if I want to express this like in sort of more of a factored form. So, oops. So we're just going to FOIL. We know how to FOIL. Just do this. So we'll get x squared, x times negative 2, negative 2 times x, negative 2 times 2 is 4. And then just clean it up a little bit here. So gather your like terms and your constants here. That is not negative 5, that is negative 1. And that will give us the quadratic that's going to go into the second part here. It would be x squared minus 4x minus 1. So this is a quadratic that is not factorable. The only way that I get what we call like irrational roots like this is I get that because I couldn't factor the the quadratic, and I had to have put it in quadratic formula and simplified as much as I could, and then I would have ended up getting these x-intercepts from the quadratic formula. This is the little way that we can sort of get the quadratic back once we have the intercept. Okay, so here is the general equation. we're going to find the family member that passes through the y-axis at the point 0, 2. So I'm just going to evaluate p at 0, which we did, same thing as what we did in the question above, because it's the point where x is 0. And I know that this will equal 2. Polynomial when x equals 0 is equal to 2. Simplify. Okay, and then just plug it back in for k. Is this still the same degree that we started with now that we found this? Or it's the same degree that the question asks us about? Is it a quartic? It is, right? Because I have two binomials that are degree 1, and I have another binomial that's degree 4. So that's, or sorry, degree 2. So that's all 4 together. So this is a quartic, so that's good. Any questions on this one? This is a little different than stuff that we've done before, this part here. Okay, so if you see these irrational zeros, this is the process. Set it equal to x, and then we want to get it set equal to 0, and I'll expand it out to find what goes into the bracket. Okay, we know how to do questions like this, but there's something a little tiny bit different about these questions that we didn't do in Unit 1, and it's this right here. We didn't do sort of like the reverse process of this. So with a 0 like this. So I have 4 x-intercepts. It would be helpful if I write the zeros and their orders. So this is a good little review from Unit 1. I've got a 0 at -2. Goes straight through, so it must be order 1. I've got a 0 at -1. It also goes straight through, must be order 1. Then I have a 0 at a half, positive half. That is also order 1. And I have a 0 at 3, which is order 1. Okay, I count up the turning points. I have 3 turning points. This is most likely degree 4. The zeros and the orders confirm that to me, so that's perfect. Okay, so let's start this in factored form. How will I create this now? Polynomial p at x is equal to what? Kenzie. Okay, this is the normal, probably what you would guess. Clayton and I talked about this before. Clayton?
Is it 2x minus 1?
It is 2x minus 1. So we don't write x minus a half. That's actually not the correct binomial that would be produced from a 0 like this. So if you're not sure, set x equal to a half, and then you're going to sort of like multiply the 2 up and bring the 1 over so that x gets isolated. So we'll get 2x equals 1, and then you'll get 2x minus 1 equals 0 to get the binomial from that intercept when you have a fraction like that. I'm going to put that over there. So this is the binomial that we want when we have an x-intercept of like a fraction like that, 2x minus 1. Actually, if you put x minus a half, you actually won't find the correct k value. It won't give you the correct shift value, and that's because it's actually 2 times x, right? So that makes a big difference with all the x's that are generated in the rest of the equation. Okay, how do I find k now? Nick? We have to plug in, okay, Surwa? Okay, any point except for these four, because we've already used those to create parts of the equation. So does anyone see a point that we know for sure is on the graph? Bella? 1, -3. Yep, that could work. I also see 2, -9. So either one of those points I think is good. I will just go with 1, -3 because those numbers are a little bit smaller. So let's plug in p at 1. And p at 1, we know from the graph, is equal to -3. So I'll get 3, 2, 2 minus 1 is 1, -2. So -12, okay. This is not 4, right? I have to divide -12 out. And then I reduce the fraction. That gives me 1/4. Okay, and sub it right back in. Okay, if you tried the x plus, or I think x minus a half instead of the 2x minus 1, you would have gotten a different value. So when you have fractions like this, we didn't practice this in Unit 1, but you just have to be careful about the binomial that you create from that. It has to be in the form ax minus b. Okay, so just a tiny little difference from what we did in our first unit. Okay? So, what time does class end today, guys? Oh, I have it right here, 12:15, perfect. So, I want you guys to try a couple of these. Perhaps you could even go and try maybe one with rational, irrational zeros. Maybe 5 is a good one to try before you leave today. 6 also has the same irrational zero type thing. I'm going to reduce these questions just a tiny bit here. Okay, those ones, the first page is pretty quick actually. We can take out 4. I'll take out 4. Actually, this one asks you to sketch. So why don't we take out, I'm going to take out 1 then, because 4 is pretty much the same thing but with a sketch. So we'll do 4. I think 5 and 6 are good to practice, and then determine an equation. Let's do, I will take out b, because b is similar from the first unit, but a is kind of like a new thing. If you feel like you need the practice with the extra questions, you can do it for sure. Okay, so we're going to say we're doing numbers 2, 3, 4, 5, 6, 7a from this worksheet. Okay, maybe try either 5 or 6 before you leave today. Or you can start at the beginning, whatever you want. It's up to you.